Good morning. This is the 19th lecture of AS and A-level chemistry lecture series. We'll talk about the rest of the group, 17 elements, and the chemistry of nitrogen in this lecture. Well, we are talking about halides. That means halogen ions. Okay, we can detect these ions in the laboratory, distinguishing which one is silver chloride, which one's silver chloride ion, bromide ion, iodide ion. You see, one important thing is that silver fluoride does not precipitate as other halides, silver chloride, silver bromide, or silver iodide. Silver fluoride dissolves in aqueous media. Therefore, we cannot make any test in the laboratory for fluoride ion in this technique. What we do, we take the halide ions in acidic media. Please mind that acidic media, we have to acidify it with dilute nitric acid. Why we should acidify the halide solution in dilute nitric acid? Because other acid will also precipitate for that anion. So we take halide ions in acidic media in a test tube and then add silver nitrate solution. We immediately get silver halide salt precipitate. That is, we get silver chloride, silver bromide, silver iodide. One more thing is that we will see that silver chloride dissolves in aqueous ammonia and become colorless solution. But silver bromide does this, but then in that case, we have to take concentrated aqueous ammonia and form colorless solution. But silver iodide will not dissolve in ammonia, and thereby we can make a clear test in the laboratory identifying chloride, bromide, and iodide ion. And then what we can see that how halide ions react with concentrated sulfuric acid. So when we take a chloride compound, that's a sodium chloride, solid, dissolve it in concentrated sulfuric acid, we get hydrochloric acid gas and sodium bisulfate solid. In this way, we cannot form pure hydrogen bromide because bromide ion reacts, oxidizes and gets bromine. Therefore, concentrated sulfuric acid is not the way to form hydrogen bromide. Okay. Iodide ions are much stronger reducing agent compared to bromide and chloride ion. And therefore, reacting sodium iodide or iodide compound with concentrated sulfuric acid, we do get iodine instead of hydrogen bromide iodide. Here are the reaction product and the type of reaction what happens when we start concentrated sulfuric acid with sodium chloride or sodium bromide or sodium iodide. In this case, we say moist hydrogen chloride gas will be produced and sodium bisulfate. This is an acid-based reaction. Here, we don't get any redox reaction here. We talked about acid-base reaction, redox reaction earlier in our lectures. Well, in case of sodium bromide and concentrated sulfuric acid, you get orange vapor, that is bromine, and then a colorless gas, acidic gas, which is sulfur dioxide. It is mainly a redox reaction in which bromide ion oxidizes to bromine, and sulfur is reduced from the +6 oxidation state to +4 oxidation state. Well, if we go to sodium iodide and concentrated sulfuric acid, a dark solid is formed, which is iodine, and some yellow solid we see that is for sulfur, and rotten gas, which is bad smell gas, which is hydrogen sulfide. So there is also a redox reaction happening. And just remind that in case of chloride, it is an acid-base reaction. In case of bromide and iodide, it is redox reaction. Here I have shown a oxidation state of sulfur and sulfur-containing compound. You know, we say in lectures, earlier lectures, all element has got oxidation state 0, and their compounds would have plus oxidation state or minus oxidation state. Sulfide ion -2, and hydrogen sulfide also sulfur having -2. But here sulfur dioxide +4, sulfate ion +4, hydrogen sulfuric acid, not sulfurous acid, +4, and there sulfur trioxide +6, sulfuric acid +6, and sulfate ion +6. I'm talking about sulfur oxidation state. Well, hydrogen halides, its reaction. Hydrogen halides are all compounds, and they are colorless gas at room temperature. The bond between this halogen and hydrogen are polar. We talked about polar bond and things like this. Hydrogen halide, that means, let's say, hydrogen bromide or hydrogen iodide or hydrogen chloride, are all soluble in water and forming strong acidic solution. Here is the reaction, how it is forming some strong solution. This, when dissolved in water, we get halide ion and oxonium ion. That is a clear, that's completely dissociated, and therefore it's a strong acid. Well, hydrogen halide with ammonia form a smoke of ammonium salt. Here you see, if we keep ammonia, base ammonia, and SC, then we see that there's a smoke, white smoke of ammonium salt. So here we have to remember that we cannot keep in our laboratory acid and ammonia in same shelf. We have to keep them separate in differential, preferably if we have space in different cupboard. Well, variable oxidation state of chloride, bromide, and iodide, we have to talk a little bit about it. Well, we know that oxidation state of chlorine is always -1, always -1. So do remember it. And then chlorine, bromine, and iodine, depending on compounds, they can have variable oxidation state. We were talking about oxoanions. What is oxoanions then? X, an element, O is oxygen. Here is a formula, a general formula of oxoanion. X, an element, and O, an oxygen atom, and Z is the charge in this compound, so-called arbitrary compound. So when we dissolve chlorine in water, we get chlorate 1 and hydrochloric acid. Chlorate 1, that is, this is a disproportionation reaction. Why it is disproportionation reaction? Because chlorine simultaneously is being oxidized and reduced. In a reaction, when we see a reactant simultaneously oxidized and reduced, we call that reaction disproportionation reaction. We can see here chlorine is 0 and here chlorine is -1, so it is reduced, and here it is +1, so therefore it is oxidized. So this reaction is an example of disproportionation reaction. Chlorate ion with the chlorate 1 ion. We can call it also chlorine oxoanions, but I would say as per IUPAC nomenclature, we call this chlorate 1 ion. Bromine reacts similarly, but then the reaction is not that vigorous. We call it in some lesser extent. In iodine is insoluble in water, hardly reacts with water. Okay, then chlorine reacts with alkali. We are talking about water, and then we are now talking about with alkali. When chlorine reacts with alkali, we get chlorate, 1 ion, and chloride ion. This is also a disproportionation reaction. Well, chlorate 1 ion again gets disproportionate reaction and getting chlorate 5 ion and chloride ion. Overall reaction is 3 moles of chlorine gas, 6 moles of hydroxyl ion, and we get chlorate 5 ion and chloride 1 ion. And bromine and iodine reacts almost similarly with chlorine, as chlorine does with alkali. A hot solution of iodine in potassium hydroxide, we get this reaction. This is the reaction. Okay, we'll go for next. We talk a little bit about the uses of halogen and their compounds. At one time, we do believe that halogen and its compounds are very much benefited for the society. For example, if we talk about drinking water, we kill bacteria passing chlorine. Pesticide containing halogen reduce loss of crops in storage. And then chlorofluorocarbons. Once it is very unreactive, and people once thought that they are completely harmless for living things. So chlorofluorocarbons are used in aerosols, coolants for fridges, halogen compounds, we use for plastics, pharmaceuticals, anesthetics, and dye stuffs. But in the First World War, first we saw that the chemical weapon used is halogen-containing compound, biological non-gases. Pesticides, if we use too much, it has a bad effect in wildlife and food chain. Earth's ozone layer, you remember this Earth's ozone layer, which protect us from harmful ultraviolet rays. It was observed that chlorofluorocarbons are is a polluting agent and a big hole in ozone layer due to this. And then people were thinking about other compounds so that we get our atmosphere more friendly to us, and therefore chlorofluorocarbon containing compounds are not using nowadays as coolant for the refrigerator, and people are investigating more and more. And now that we say that we could reduce the hole in the ozone layer by using other chemicals, and these chemicals, pesticides, chlorofluorocarbon, are now less and less using, and in many cases, in many countries, these are banned. Now we go to, we have completed our chemistry of group 17, that's halogen chemistry. Now we talk about chemistry of nitrogen. Well, nitrogen is a diatomic molecule, and its atomic number is 7. We know it from the periodic table, and it is the 5th element in period 2 and first element in group number 15. Nitrogen is in the AS level syllabus. So we talk about a little bit of nitrogen, and we know that this non-metallic gas is about 78% in our Earth atmosphere, and it's very unreactive. Why it is unreactive? If we look to the electronic configuration of nitrogen, we see that the valence shell electron has got only 5 electrons. So we can have a dot and cross diagram like this for nitrogen. And if we take two, we said it is diatomic molecule. How the bond is formed in diatomic nitrogen molecule. That's what we showed here with the dot and cross diagram of two nitrogen atoms. And we can see that we can get an inert configuration by using this, sharing this three electron of this nitrogen atom and three electron of this nitrogen atom. And therefore we get triple bond. If we remember, we have in this triple bond, we have one is sigma bond and two are pi bonds. And then we have two lone pairs, lone pair of electrons. That is all the bonding in diatomic molecule and nitrogen can be explained. It has got a very high bond energy, about 1000 kilojoule per mole. Therefore, it is the bonding is very strong and it is unreactive. But though it is unreactive, in extreme condition, nitrogen gets reacted with oxygen. In the upper atmosphere, due to thunderstorm, these unreactive nitrogen react with oxygen and forming nitrogen oxides. And first it forms nitrogen 2 oxide, and then further oxidation it forms nitrogen 4 oxide. And in the water droplet in the atmosphere, it reacts with it and forms nitric acid in the atmosphere. Well, this is a part of the natural nitrogen cycle. And from there, we get nitrate ion, and which is a usable form of nitrogen. That nitrate ion in dilute nitric acid make proteins. And these proteins are essential for the healthy growth of plants. Here I show you a slide with different types of compounds of nitrogen. We say diatomic nitrogen, inert, but under extreme condition it reacts, and we see that it forms ammonia, a very important compound for our fertilizer, etc., hydrazine, and then ammonium salt. Then also nitric acid, we talked about it. Nitrogen dioxide, we talked about it. Nitric acid, we talked about it. And then nitrate salts and nitrite salts. This is a schematic diagram, how many different compounds of nitrogen we can get in our chemistry. With these slides, I'll finish our lecture. Ammonia is, I said, it is a very important compound. It is only common alkaline gas. Here are the dot and cross diagram of ammonia. That is nitrogen, hydrogen, covalent bond, nitrogen, hydrogen, covalent bond, nitrogen, hydrogen, covalent bond, and a lone pair here, lone pair of electrons. We do talked about dative bonding. You see, this is ammonia, and we have a lone pair here. And with the proton, it can form bond, and this bond is called dative bond. And if you remember, we said a dative bond, how it has happened? A lone pair of an atom will be shared by an empty orbital of another atom, and that makes a dative bond. Here we show the dative bond of ammonia. Ammonia is a very important compound, and industrially, tons of millions of tons of ammonia is produced industrially, and that's why we produce by nitrogen gas and hydrogen gas, and the catalyst and a certain temperature gives us ammonia. And ammonia is an example of weak base. Here is the reaction we showed how we can talk about weak base. Well, in the next lecture, we talk a little bit of ammonia more and show how we can prepare ammonia gas in the laboratory. So up to this, we talk about chemistry of nitrogen, and we will continue chemistry of nitrogen in the next lecture. Thank you very much for your patience.